Hello, everybody. Welcome to our first remote learning lecture, and this is going to be on relative dating. I know most of you guys probably have already had this lecture before, but this is going to be most likely a review for most of you. At least for the very first part. I think the last part we haven't done yet in class, so just pay attention. Along with this lecture, you will have a lecture outline. Now, this lecture outline will serve as your outline, as well as where you could actually write it notes. You could also hole punch this and include it with your notes. It's a good way to study for your upcoming test. So let's get to it. All right. So what you should do now is, if you haven't done so already, give yourself like us. You could pause this video and print this out so that we can go along line by line. And so do that now. And all right. Let's go with the first one. Number one, geologic time. Now, geologic time is the long period of time occupied by Earth's geologic history. It's really called geologic time because it's really the history of the Earth, what occurred in Earth's history over a long period of time. Like we said, we already had the discussion in class regarding the age of the Earth. Again, so let's not have this discussion again. This is pretty much just passing the regions. And so let's move on to the first one, relative dating. Now, relative dating, as you know, is the method used by geologists to place rocks in chronological order. It really identifies what rock comes first, second, third, and so on and so forth. All right, so there's actually few principles or laws that geologists use to chronologically date rocks or rock units. First things first is the law of superposition. Now, most of you guys, like I said before, know what law of superposition is. If I told you that if you have a stack of newspapers, which newspaper, if you assume the newspapers weren't disturbed, which part of the newspaper would you find the oldest edition? You'd probably say the very, very bottom. So, which is true also for rocks. If rocks were undeformed, for example, you have sandstone, shale, and limestone right here, you can assume the top one is the youngest, the bottom one is the oldest. The bottom one here is a picture of this particular one in real life. Again, you can see that the limestone on the bottom is the oldest, and the top part, which is the sandstone, is the youngest. B. Principle of original horizontality. This states that sediments are deposited in horizontal position. If you see rock layers that are still in a horizontal position, it means that they have not been disturbed. What does that mean? It means this. If I were to say which of these two rock layers are older, you will say this one. Well, that's not true. You can't even say that. But I would just say that what would happen is that rock layers are always deposited in horizontal manner, especially sedimentary rocks. And if they are deformed in any way, it means that that deformation occurred later. So therefore, if you see a deformed piece of rock, that means that that event happened later than its original depositing. Hence, original horizontality. All right, next page over. Let's take a look at C. This is the principle of cross-cutting relationship. Remember, we did some of this in class. So it means this: when a fault cuts through rock layers, or when magma intrudes rock. You see we have both of them here. We have an intrusion. We also have a fault. So we're going to put both of them in play. It means that the intrusion or the fault is actually younger than the rocks around it. That makes sense too, because how can you make a fault in a rock that it's not there, obviously, right? Or how can you create a magma intrusion in rock that isn't there? So therefore, the intrusion has to be younger than the rocks around it, or the fault has to be younger than the rocks around it. But what happens if you have both? Well, again, let's take a look. Notice that D is broken by E, which means that D must have been there and E came after to break it apart. Okay, that could be also vice versa. If the fault is there, but the D, if intrusion D runs straight along without being broken, it means that intrusion D came in after the fault. Okay. All right. So here we're to list the following order from oldest to youngest. You have rock units A, B, C, D, and fault E. And so I've gone ahead and put the answer for you. C is the oldest. It's in the very bottom, which means according to law of superposition, that's probably going to be the oldest, probably. The next one is B, A, and finally D cut across rock units C, B, and A. You can see it there. But, so therefore it's then older than, it's younger than all these three rock layers, but E came about last to break D as well. So now E is the youngest in this case. Fault E anyway. All right, which brings us to the next one. Inclusions. What are inclusions? Well, these are pieces of rock that are contained within another rock. Normally, when you're when you're relatively dating rock layers, any rock that contains inclusion is younger than the two. For example, let's take a look at two rock layers. You have an igneous rock, and then you have a rock layer in the top. What happens is that the rock layer was removed, and then new rock layers formed, creating an inclusion between the older rock and the new rock. By the way, that's a nonconformity. We'll talk about that later. And notice that there's inclusions contained within that rock, which means that rock came in after or later. All right, the next page over. Let's take a look at unconformities. Now, what is an unconformity? Unconformity is a break in a rock record. It indicates a long period which deposition stopped, erosion removed rock layers, and deposition resumed. So which means that you have rock layers are forming, rock layers removed, and then new rock layers form on top of that, creating an unconformity in between the two. Okay, so you can see here, there's three kinds of unconformity. You have disconformity, angular unconformity, and nonconformity. So every time you see that jagged line between rock layers, you can see it there, you can see it here. This is how usually the Regents draws unconformities, so it's easily seen there. All right, so how do we, so what is disconformity? Disconformity is pretty much between sedimentary rocks. You have layers of sedimentary rock, and then deposition stopped, erosion removed a chunk of those, a bunch of layers, one layer, two layers, who knows, many layers of sedimentary rocks, and then deposition resumed and new rock layers formed on top of that. So that's why you have what we call a disconformity. Now, how many rock layers are removed? At this point, just by looking at it, you can't tell, but later on I will tell you how geologists can tell. What's an angular unconformity? An angular unconformity occurs when you have deposition of sedimentary rocks, and then some sort of an event where rock layers get pushed upwards to create a fold. I think we spoke about folds before, and then the erosion removed the folds, kind of like just removed them, and then new rock layers went on top of it. So you can see the fold there, then you have erosion, and then deposition on top. By the way, those are, and you can see that there's some inclusions right there. So what is a nonconformity? A nonconformity occurs when you have the bottom part is either a metamorphic rock or an igneous rock. The reason why it's a nonconformity is because igneous rocks and metamorphic rocks don't really form layers. So you really can't see the layering effect. So you don't know the age below this. There's no layers. So it's just most likely a magma chamber that got exposed and was eroded, and then new rock layers formed on top of it. Okay? All right. So as I mentioned before, well, how do they know what's missing? Well, there is a way they could tell. It's not a foolproof because, as you know, a lot of time has passed, and erosion will erode as they do. All right. So what we do is we go to correlating rock layers. Geologists could actually determine the relative ages of rock layers in one formation. Right here, you could tell, right? Bam, bam, bam. This, then, bam, bam. Yeah. But what happens when you have rock layers that are in one location, but they're the same? How do you correlate rocks from different places? Well, to do that, geologists actually developed a system called correlating rock layers. What they do is they obviously will try to match up the types of rocks that are layered, but also they need something like an index. In this case, they use fossils, like index fossils. Index fossils are very good because they're actually a type of fossil that only lived on Earth for a very short time. But, and they were distributed over a large area. And then they went extinct, which means that if you're looking for their fossils, they'll only be found in one layer only. And they will be found everywhere, only in that particular layer. All right, so that's why there are many types of index fossils that geologists use, depending on obviously the area. But the index fossils are a great way to correlate rock layers. Again, they exist for a very short time and distributed over a large geographic area. So, but anyway, technically, any event that occurs over a short time and distributed over a large area could also be used as an index. For example, volcanic eruptions. Back in the beginning of Earth's days, there was many volcanic eruptions that erupted and spewing copious, large amounts, enormous amounts of ash over a large area, and then the volcano goes extinct, and then the ash will remain in the ground, and new layers will trap it in between, and so therefore those layers you could correlate them because they happen at the same time, much like the index fossil, they happened roughly about the same time. So, how do we correlate rock layers? And here's an example. In this case, we're going to be using the volcanic ash as a correlator. For example, you see the volcanic ash in outcrop A, volcanic ash in outcrop B, and volcanic ash in outcrop C. So if you were to line these up, if you were to draw a line to line them up, it means that what happens after volcanic tan limestone, you can see tan limestones over there. And what happened before is the green shales over here, and the green shales over there. So my question here is, well, which outcrop contains the youngest rock layer? Well, it's going to be outcrop A. Which one? Tan siltstone, because you see that if you were to actually line this up, you're going to see that tan siltstone will be the one in the very, very top, and you're going to say to yourself, well, why don't I see siltstone in B and C? Well, they've been eroded away all the way here in this conglomerate that actually correlates. This conglomerate correlates over there, and this brownstone should have been up here. This brown sandstone is here, so it should have been up here as well, and obviously there are subsequent layers up there. Okay, now you could use volcanic ash. Again, geologists actually also use any index fossils that are contained within the outcrops as well. All right, finally, let's just do a little backtrack. Let's see if we could date these last things that are occurring here in these last three layers from youngest to oldest. Gives us some time to do it. You could pause the video, obviously. You could do that every time. See if you can do it yourself. But the answer is gray limestone being the one on the very bottom, the red sandstone above it. And then unconformity occurred. And then, did I forget the intrusion? Well, whatever. It should have been the intrusion, the gray siltstone, the intrusion, then fault X or Y. So that should have been gray intrusion. I know you're just thinking that, hey, wait a minute, we don't have that in ours. Well, you could write it in. The gray intrusion happened, and then the fault cut it. All right? Okay, everybody. Normally there would be an assignment attached to this, but this was, last minute. I had to prepare a last minute lesson, and I ordered the book, and I know some of you guys probably left your book in school. Don't get it. I've already got another one, and I'm going to be sending you guys assignments from that book for you guys to do. All right, so that's pretty much it, everybody. See you tomorrow. Well, speak to you tomorrow.